This problem was number 4 on the 2013 AP Physics B exam, the free response section. We've got this sort of modified Atwood machine going on, and boy oh boy do they love Atwood machines on the AP exams. Definitely problems to know how to do. And you know, they're good problems to ask about because they really do include multiple concepts that we have to understand in order to solve them. So in this one, we've got this little cup that's holding a ball on top. And so this block is going to get pulled over by this weight hanging down. And when it gets to this position right here, there's some stopper that makes the block stop, makes the cup stop, and the ball, due to its inertia, is going to continue moving on. It's going to be launched horizontally and travel like a projectile until it hits the ground 1.8 meters out. So our first question is about finding the speed of the ball just as the block hits the bumper. So that's the speed right when this ball leaves the cup and starts acting like a projectile. So there's a couple of different ways that we could potentially go about this problem. If I look over here, I see 0.95 meters. That's a distance from here to here, or a displacement from those 2 points. I know that this mass starts from rest, so I've got an initial velocity. That's two of the kinematics quantities right there. So if I could find another one, a third one, I might be able to solve for that velocity when it gets to this point. And so I start thinking, well, okay, maybe if I know something about forces, I could figure out acceleration, and that might be a way to go about this. Well, I could figure out the force, the net force acting on this system is just gravity pulling down on the 2.5 kilogram weight, and there's no friction here, so I don't have to worry about that. But I don't know how much that's going to make this whole system accelerate, because I don't know how big a mass this is. And we can't just use the mass of the 0.3 kilogram ball, because it's the 2.5 kilograms and the ball and this mass that are all moving under the influence of that one force of gravity. So I don't have enough information to find acceleration there yet. So instead, let's think about this from a projectile point of view. I have the ball launched horizontally. It travels a horizontal distance of 1.8 meters. It falls 2.4 meters. How much time is it going to take to fall, or rather, how fast is it going to leave the cup to land at that position? So always a good idea here to organize your information. So we'll have information in the x direction and in the y direction. So if we look at our initial position and final position, and initial velocity and final velocity and acceleration, and then remember, time is the only one that doesn't get divided up into x and y separately. X acceleration for projectiles is 0, and for y direction is negative 9.8 meters per second squared. That ball would be launched horizontally. We're looking for that initial speed that it was traveling at, but we know in the y direction it'd be going at 0 meters per second because it's launched horizontally. It starts up at a height of 2.4 meters and ends down at a height of 0. And we'll say it starts at an x position of 0 and ends at 1.8. Okay. So over on the x side, we don't have enough information to solve for initial velocity right now. If we plug anything into equations, we'll just find non-useful answers on that side. So we first need to work on the y side, and we're going to use time as our bridge between x and y, as we often do in these problems. So let's figure out what we can do with that to get time. So I need an equation that has time in it. I've got the everything except the final velocity in it. So that tells me the equation I'm going to want to use here is the y equals y naught plus initial velocity in the y times time plus 1/2 acceleration in the y times time squared. And here our y is going to be 0, and our initial velocity in the y is going to be 0 as well. So we just got 0 is equal to 2.4 meters plus 1/2 times negative 9.8 meters per second squared times t squared. So I'll move the 2.4 over to the other side by subtracting. I'll multiply the 1/2 and the negative 9.8, so negative 4.9 meters per second squared times t squared. Divide both sides by the negative 4.9, and we get 0.4898, and that's seconds squared is equal to t squared, and then square root both sides, and we get the time it takes to fall is 0.70 seconds. Okay, and then we know in the 0.70 seconds it travels a horizontal distance of 1.8 meters. So now we can use that same equation, but in the x direction. So x naught plus v naught x times t plus 1/2 ax times t squared. And acceleration in the x, that goes to 0. X naught goes to 0, so this becomes x equals v naught, which we're looking for, times t. And so our x is going to be the 1.8 meters is equal to v naught x times 0.7 seconds. And so v naught x ends up being 2.6 meters per second. The next question asks us about the acceleration of the block as it slides across the table. So now we come back to our original line of thinking. We knew that it started at rest here. It ends now at a speed of 2.6 meters per second, and it travels a distance of 0.95 meters to do that. So we can do this with kinematics again. So Vx, the final velocity in the x squared, is equal to the initial velocity in the x squared plus 2 times acceleration times the distance traveled, x minus x naught. So we got 2.6 meters per second squared is equal to 0 plus 2a, and then that distance was 0.95 meters. So this will be 6.76 meters squared per second squared is equal to 1.9 meters times the acceleration, and divide both sides by the 1.9, and we get 3.6 meters per second squared. All right, calculate the mass m of the block here. So we were thinking about this a minute ago, using forces to analyze this situation to move the block over 0.95 meters. So what we want to do with this is we're going to treat this whole collection of objects as one system, one big mass, and the only force that isn't an internal force that acts just between the objects as part of that system. So the only external force is this force here, the mass, the 2.5 kilograms times the 9.8 meters per second squared. And there's no frictional force resisting this motion. It's only this one gravitational force that causes that acceleration. We know that all three pieces, the ball and the block and the object that's hanging down, those all move together. So maybe redraw this. This will be the block and the ball and the object that's hanging, and those are all being pulled by some force that's equal to the mass of the object times gravity. And it's okay that there's a bend in there, that two of our objects are moving horizontally and one that's moving vertically. Since they're all connected, they're all going to move at the same rate. So we don't really need to take that into account here. We can think of our coordinate system as being bent along with it, I guess. So now we use Newton's second law. Net force is equal to mass times acceleration. Our net force, the only force acting on this, is the mass of the object times gravity, and that's equal to, well, that'll be the mass of the object plus the mass of the block plus the mass of the ball. All of those things have to be accelerated times their acceleration. Alright, so we got 2.5 kilograms is the mass of the object times 9.8 meters per second squared is equal to 2.5 kilograms plus the mass of the block they just call capital M plus the mass of the ball was 0.3 kilograms times the acceleration we found in the last part was 3.6 meters per second squared. And now all we need to do is solve for M. So this is 24.5 newtons, and that's equal to 2.8 kilograms, the 2.5 plus the 0.3 plus M, times our acceleration, 3.6 meters per second squared. We'll divide both sides by the 3.6 meters per second squared, and we get 6.8 kilograms over here. Remember, Newton means kilogram meters per second squared. Divided by meters per second squared, we just have kilograms left. It's equal to 2.8 kilograms plus M. Subtract the 2.8 from both sides, and we get 4 kilograms for the mass of the block. And the last piece. As the mass of the ball is increased, the horizontal distance it travels before the hitting the floor will decrease. Why does this happen? Well, if we come back to this situation, we can see that the net force on this system would be unaffected by changing the mass of the ball. All that matters there is the mass of the object and the free fall acceleration of gravity. But the overall mass of the system would be affected. So if force remains constant, but the mass grows, the mass increases, then acceleration must decrease. So here, our acceleration as the block is moving over in this direction, that has to decrease, which means that as it moves this fixed distance, it's not going to reach as fast of an initial velocity. So here, the initial velocity is going to decrease. And since that velocity has nothing to do with how much time it takes to fall, it's only the fact that it starts with an initial velocity in the y direction of 0 that makes it take 0.7 seconds to fall. The time to fall won't be changed, and so the distance, that's x minus x naught, that was just equal to the initial velocity times the time. Well, the time stays the same. The initial velocity falls because acceleration fell here. So that means the distance traveled is going to decrease as well.